Hi, my name is Luis Guzman, and I'm going to be presenting the paper Robotic Embodiment of Human-like Motor Skills via Reinforcement Learning. So the main problem that we're looking at is that certain tasks are still really difficult for robots to accomplish, especially those that require human-like dexterity. So we're trying to see if we can use human demonstrations in order to teach robots some of those more difficult tasks. So the main contributions of this paper are incorporating human and robot actions using reinforcement learning. And we implement this on a Kinova Gen 3 robot and complete a block pushing task. And we also make some improvements over existing baseline methods. So this is the actual environment we use to train the algorithms. It's modeled in MuJoCo, and we have two different robots. One of them is a 5 degree of freedom robot, and the other is the 7 degree of freedom Kinova robot. There's a green target point in each environment, and this represents the point that the robot needs to reach using its end effector. Then there's also a blue obstacle that the robot needs to avoid at all times. And so the agents are first trained on stationary goal points, and then afterwards they're trained on the expert trajectories. And this is done by copying the network weights from one environment to the other. And this is known as transfer learning. So in order to get the actual expert trajectories, we use a Vicon motion capture system. This is an array of cameras that is able to locate reflective trackers in 3D space. So as the expert is completing different tasks, we know their full joint angles and the location of their hand at all time. And so since we're using reinforcement learning, we also create a reward function and an observation space. The reward function consists of minimizing the distance to the target point, avoiding collisions, and also preferring small movements so that we don't overshoot the target. The observation space consists of the robot joint angles and then also the locations of the target and the obstacle. And we make some improvements here over the baseline, and these are detailed in the paper. And so these are our results. We compare 6 different reinforcement learning algorithms on this environment. And we find that the best performing ones were TD3 and PPO. And so these are the two that we focus on for the rest of the paper. This is what the policies look like after they've been tuned on the expert trajectories. The green point here represents an actual trajectory from the Vicon system. And so this is the hand location of the expert. And the PPO policy is on the left, TD3 is on the right. And the robot has learned how to position its joint angles in order to optimally reach the expert's hand location while also avoiding the obstacle. And one thing you may notice is PPO is generally more stable than the TD3 policy. So even though TD3 got a higher reward value, we may prefer PPO for more stable trajectories. Lastly, we implement this policy on a physical Kinova robot. And this is a demonstration of the expert showing the robot how to push a block across the table, and the motion is successfully copied to the physical robot. So in the future, we'd like to use this system to replicate all joint angles of the expert to the robot, not just the hand location. And we'd also like to use recurrent neural networks in order to enable different phenotypes of robots to learn using this system. So thanks for listening.